Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Center for Reliable and High-Performance Computing. The title of my talk today is Enhancing Security of Real-World Systems with a Better Understanding of Threat. So before getting into the main body of my talk, I would first like to give an overview of my research experiences. The focus of my dissertation is security threat analysis and mitigations in real-world systems. Broadly, I want to answer three questions. First, how errors in hardware and software impose security threat to real-world systems? Can we identify any common characteristics among security threat? And secondly, how effective are current defense techniques? Are there any substantial deficiencies in our current defense techniques? And finally, how can we build better defense techniques? So I think the most unique aspect of my research is the analysis-centric research approach. So I spent a large amount of time throughout these years to analyze security threat in real systems. In my first two papers, we started hardware memory errors in order to evaluate their impact on system security. And then we try to understand software vulnerabilities. So we did an extensive analysis on Bugtraq and CERT vulnerability databases, as well as a large amount of source code of vulnerable applications. Then recently, we focus on the analysis of current attack method and defense techniques. So the goal of all these analysis is to expose new security threats which motivate us to develop new defense techniques. So many areas in computer science are related to my dissertation, including security, dependability, and formal method, operating system, and programming language. So besides the research in Illinois, I also have several system hacking experiences in industrial labs. So the first project in Avaya Labs was to port libsafe to Windows system. The libsafe is a software package originally designed for Linux to defeat buffer overflow attacks. Then in summer 2002, my project in Bell Labs was to hack FreeBSD TCP/IP implementation and network card drivers in order to detect and defeat network denial of service attacks. Then I did my first MSR internship with Dan Simon on audit enhanced authentication in Kerberos. This project requires modifications on Windows kernel security subsystem, Kerberos, and local security authority, and anti-DLL. And last summer, I worked with John Dunnigan, Chad Verbowski, and Yimin Wang to develop a tracing technique to identify the dependencies of Windows applications on administrators' privilege. And this project requires a substantial development work on Windows kernel security subsystem, access and privilege checking, as well as a good understanding of application interaction with Windows kernel. So those are interesting projects that I want to talk to you during our one-on-one meetings. But in this talk, I would like to focus on my dissertation. So, the first part of the talk will be focused on analyzing and identifying security threats on real-world systems. So I will first briefly illustrate how the security of real systems can be compromised due to hardware and software memory errors. Then our analysis on many real security vulnerabilities indicate that a type of memory corruption attacks currently believed to be rare is in fact a realistic threat to the system. Then I will discuss how this finding affect the effectiveness of many current defense techniques. Then, in response to the new threat, we propose new defense techniques towards a better security protection. So in the second part of the talk, I will define a program behavior which we call the pointer taintedness, which is a common characteristic of memory corruption attacks. Now, based on pointer taintedness, we built a theorem-proving based program analysis technique and a runtime detection technique to defeat most memory corruption attacks. So now, now I start my first part, analyzing and identifying security threat on real-world systems. So it is widely known that hardware memory errors can cause dependability problems, for example, system crash or erroneous computations. We are interested to know how likely that hardware memory errors can cause security problems. So we emulated random hardware errors and evaluate their impact on security. For example, when there is an error in the user space, then the authentication can be bypassed. The authentication of FTP and SSH can be bypassed so that an attacker can get into the server. And we also observe that if there is an error in the Linux kernel, malicious packet can penetrate the firewall without being detected. So these indicate that with a non-negligible probability, real systems, the security of real systems can be compromised due to random hardware errors. According to our experiment, that is usually from 0.5% to 2%. In that, yes, yes, yes. Pardon? Okay. Okay. Yeah. So this is an interesting work which motivates researchers in another university to actually conduct physical fault injection experiment. They are able to show that the Java type system can be completely subverted due to random hardware errors. They actually use a spotlight to heat CPU to introduce physical memory errors, and they are able to show that Java system can be subverted. So now let's talk about software vulnerabilities, because although hardware memory errors are potential security threat, the most imminent security vulnerabilities are due to software bugs. So then our statistics on CERT adversaries, by the way, this is a vulnerability database. Our statistics shows that over 66% of vulnerabilities are due to low-level memory errors, which include buffer overflow, integer overflow, heap corruption, format string vulnerabilities, and recent globbing vulnerabilities. So these vulnerabilities are widely exploited by attackers, worms, and viruses. Let's see an example. This is a classic attack against Washington University FTP server. So first, when the attacker authenticates to the server is running as a regular user. Then the attacker, when the server gets into the service loop, the attacker can embed malicious content in the input, which is later used by function printf. And at this point, the attacker gets a chance to overwrite an arbitrary memory location. So in this case, the attacker can overwrite a return address to hijack the control flow in order to run a piece of malicious code. So by calling set effective UID 0 and exec being sh, the attacker get a root shell. So very similarly, to attack an HTTP server program, the attacker can first overflow a heap buffer, which corrupt the heap structure. Then, when this buffer is later freed, the attacker gets a chance to overwrite a memory location. In this case, the attacker can overwrite a function pointer to hijack the control flow. And still, the attacker gets the root privilege. Now, the underlying principle of all these attacks is to exploit memory corruption vulnerability in order to corrupt control data to hijack the control. By control data, I mean very specifically the data used as target of call, return, and jump. They are widely understood as security critical elements. So according to CERT and Microsoft Security Bulletin, control data attack is the most dominant form of memory corruption attacks. So, so accordingly, many current defense techniques are designed to enforce program control flow integrity in order to provide security. For example, many intrusion detection systems are based on a system call monitoring to detect any anomalies of your program behaviors in terms of system call sequences. And also, some other techniques strictly prevent you from overwriting any control data. So all these techniques are effective against control data attacks. On the other hand, however, that attacks not corrupting any control data, or we can say non-control data attacks, they are currently very rare in reality. We are aware of a number of instances suggested in the literature. For example, one instance suggested by Yang and McHugh in 1987. However, there is no study to understand how applicable are such attacks against real-world systems. But that is a very important question because this may affect the effectiveness of our current defense techniques. So, in fact, the general applicability of non-control data attacks depends on whether attackers are really incapable to mount such attacks against many real systems. So based on our previous hardware fault injection experiment, we have seen that given a memory error, it is likely that the security of real system can be compromised. So maybe the attacker's capability is more powerful than we are assuming currently. So in particular, we know that even random hardware errors can subvert the security. And compared to hardware memory errors, software vulnerabilities are more deterministic and more amenable to attacks. In addition, we have seen that each attack exploiting software vulnerabilities can be decomposed to multiple primitive components, just like a sequence of gears where you can assemble the attack, allow you to construct polymorphic attacks. So in other words, the current attacks overwriting control data can be easily transformed to attacks not corrupting any control data by exploiting the same vulnerability. So based on this insight, we claim that many real-world software applications are susceptible to non-control data attacks, and the severity of the attack consequences is equivalent to that due to control data attacks. Now, of course, we need to validate this claim because now we are not talking about hardware fault injection. We are talking about purely software attacks. This claim is validated by constructing non-control data attacks to get the root privilege on major network servers, including FTP, HTTP, SSH, and Telnet servers. We found that vulnerabilities in these types of server applications account for over 1/3 of vulnerabilities in CERT adversaries. So these are a reasonably representative set of real applications. So the importance of our claim is that it clearly indicates that non-control data attacks are realistic threat. So let's see some real examples. Again, Washington University FTP server. This is the most widely used FTP server. There is a format stream bug. There is a format stream bug when you call this function, getFTP command. So all existing attacks are control data attacks. And in our study, we found a way to get the root privilege of FTP server while still preserving the control flow integrity. So the challenge of us as attackers is that when the user authenticate to the server, and here we have an integer x, which is the user ID of the authenticated user. So in this case, assuming x is 109, which is the regular user ID. Then the server calls set EUID to job the privilege to the regular user's privilege. So now the question is, how can we exploit the vulnerability to get the root privilege? So then, to get the root privilege after this point. So what we can do is, first, we send a special site exec command, which can trigger the format string vulnerability to overwrite integer x to 0. And after that, we force the program to go through a very specific execution path. Eventually, the function getDataSock will be invoked. Then, in the function getDataSock, the privilege of the process needs to be temporarily elevated in order to make this system call, because this is a privileged system call. And after that, the function tries to job the privilege to the regular user's privilege. However, since we have already overwritten x to 0, so this function call does not job the privilege. So when the server returns to the service loop, it is still running as root, allowing me to upload an arbitrary file, including etc password. So I can overwrite this file, which means I can grant myself the...
So just figuring out what this is a buffer overrun vulnerability?
You're
just exploiting not far enough to hit the control structure. You're just exploiting far enough to hit the local variable.
Yeah. The idea is this, but in this particular case, it is a format stream bug, which allows you to specify a memory location to write that. Yeah.
%n or whatever.
%n, yeah, exactly.
Okay.
So we can grant. I can grant myself the root privilege, and as you can see that throughout the entire attack process, I do not overwrite any control data, but only the integer x. So this is not a control hijacking attack. And to attack an HTTP server, we found that overwriting only 4 characters or 4 plain text characters is sufficient to get the root privilege. So in this attack, we corrupt the configuration string of CGI bin path. So what is CGI? CGI is a standard interface for clients to execute a piece of to execute a set of pre-selected executables on the server side. So and CGI bin is the specifies the root directory of the executables that you can run. So any executables outside CGI bin path cannot be executed. So suppose in this case, suppose the server name is www.foo.com and the CGI bin is user local http://dexe. Then when the client makes this URL request, the server will first take the CGI bin configuration append by /bar to run this file on the server. So you can realize the importance of the integrity of CGI bin. Our attack is to exploit the heap overflow bug to overwrite CGI bin to /bin, so that when I make this request, the server will execute /bin/sh as root, which still gives me the root privilege. So I only corrupted a CGI bin string from this string to this string. So this is not a control flow control data attack. Another example, a real example, is a widely used SSH server developed by SSH Communications. There is an integer overflow bug to in this file, in this function. Sorry. So we observe that there is a stack integer auth, which is a flag to indicate whether the user has succeeded in the authentication. So initially, auth is 0. Then the server tries to authenticate the user. So in this case, for example, when I try to send the password, this function will be invoked. However, so of course I do not have the correct password. However, I can exploit the vulnerability at this point to override auth to 1. And after that, the server will break out of the authentication and let me get in without correct password. And more examples include the default Telnet server of Red Hat Linux, where we can override 2 strings from login to sh, from this to -p. Then we can get the root privilege. Also, to attack another HTTP server, we can exploit a stack buffer overflow bug in order to embed malicious content /.. in the URL. And once you can embed /.. in your URL, you can execute any files on the server side. So the success of all these experiments clearly shows that control flow integrity is not a sufficiently accurate approximation to software security. And so you may notice that usually non-control data attacks are very specific to application semantics. For example, the CGI bin attack does not work for FTP server. It only works for HTTP server. However, in our study, we found that many types of non-control data are critical to security, which can be overwritten by attackers. Therefore, this is the danger. Once attackers have the incentive, they are likely to succeed in non-control data attacks. And so being aware of the general applicability of non-control data attack, we now re-examine current defense techniques. We found that many of them are based on control flow integrity. For example, they either monitor system call sequences, or they protect the control data from being tampered with, or they implement non-executable stack and heap. All these techniques are effective against traditional attacks, but not non-control data attacks. Now, another technique is pointer encryption. So this technique, currently, it can only protect pointers at the application level. And as you can see that in my previous attacks, none of them overwrite any pointer at the application level. So which means in order for this technique to be effective, at least it has to encrypt. Right? Oh, I'm sorry. So the stack. No, in my case, the example of stack buffer overflow, I only overwrite within the current function frame. I do not exceed the boundary, because if I overwrite through the return address, I will be caught. So I have to restrict myself within the current. Yeah. So so in order for this technique to be effective, at least it has to encrypt pointers at C library level to defeat the attack. However, that is very challenging because at C library level, usually there is no sufficient type information, and type casting is very often. And more importantly, in libc, performance is a critical issue which prevents you from doing encryption and decryption very often. And then another technique is address space randomization. So this is a good idea which forces program memory layout to be always different in each run of the process. However, it is also challenging to deploy this technique in each program segment. So currently, people are still implementing this idea segment by segment. Moreover, even when address space randomization can be deployed to every program segment, a recent paper in the CCS conference shows that the deployment of this technique on 32-bit architecture does not provide sufficient entropy to defeat brute force attacks. And finally, the techniques like stackguard, libsafe, and format guard, their effectiveness are not affected by non-control data attacks. However, these techniques are very specific to stack buffer overflow and format string attacks. They are not generic solutions. Therefore, we argue that building a generic and secure defense technique is still an open problem, and the future defense research need to address this realistic threat more seriously. Yeah, if we can achieve type safety, then the situation will be much better. But I think the common belief is achieving complete type safety is pretty challenging task. Yeah, but we are getting there, I think. So we know that we know that we cannot rely on control flow integrity to build our defense techniques. The next question is whether there exists such a common characteristic among memory corruption attack that allows us to build our defense techniques. So in this part of the talk, I will first define a program behavior called pointer taintedness, and then I will show that detecting pointer taintedness is a promising direction towards a better security protection for real-world systems. Now, first, what is pointer taintedness? Pointer taintedness is a program behavior where a pointer value, including a return address, is derived from user input. Now, in the next slide, I will show that many memory corruption vulnerabilities, many memory corruption attacks are due to pointer taintedness, which allows the user to arbitrarily specify the memory location to read, write, and transfer control to. So this pointer taintedness usually is a pathological program behavior caused by security attack. And the strength of the notion of pointer taintedness is that it provides a unifying perspective for reasoning about many security attacks, including format string attack, stack buffer overflow attack, heap corruption, and globbing attacks. So now I will show a few examples of this. Maybe I think the most widely known attack is stack buffer overflow, where I have a stack buffer with 100 bytes. Then when the program calls string copy, the user input can exceed the boundary to override frame pointer and the return address. So in other words, the root cause is is because frame pointer or return address can be tainted. Then a more complicated example is format string attack. So here I have a piece of code to read a string from socket and print out this string. Although the correct invocation of printf should be %s buff. And this is an instance of format string attack, which allows the attacker to overwrite an arbitrary memory location. In this case, I will show you how to overwrite the memory location AABBCCDD. The only thing the attacker needs to do is to send this string to the buffer, which is placed on the stack. And then when printf is called, eventually a child function vfprintf will be invoked. And in vfprintf, there are 2 pointers. The first is the format string pointer to scan through the entire format string. And another pointer is AP, the argument pointer, to scan through the argument list corresponding to the format directives. So there are many details in format string attack, but the most crucial fact is that when FMT points to %n, AP happens to point to this word, which is specified by me. So the behavior of vfprintf is that whenever FMT points to %n, then **AP equals character count. So effectively, this statement is *AABBCCDD equals character count, which allows you to write a value to a memory address specified by the user. So the root cause of format string attack is because *AP is a tainted value which is dereferenced. So another example is the internal of heap corruption attack is because so the free memory chunks are organized by the heap management system as a doubly linked list. So in this case, free chunk B has a forward link to A and a backward link to C. Now, if for any reason that these links can be tainted by user value, then when the allocated buffer buff is freed, these 2 statements will be executed. So now we know that if BFD and BBK are tainted, then the effect of free is to write a piece of user input, a piece of data from user input to the memory address specified by user input. So basically, you can write an arbitrary value to an arbitrary memory location. So this is a severe memory corruption. Now we have seen so many real examples of pointer taintedness. Now the question is, how can we build defense techniques to defeat these attacks? So in the rest part of the talk, I would like to I will discuss 2 techniques. The first is a static code analysis technique to formally reason about pointer taintedness in order to extract the conditions under which such possibility exists. And the goal is to uncover potential vulnerabilities. The other technique is a runtime detection technique to monitor at runtime whether a tainted value is dereferenced as pointer. So this is to defeat memory corruption attacks. In this project, we developed a theorem proving based analysis technique to formally reason about pointer taintedness. And currently, this technique is used to extract security specifications of library functions. So we found that a significant portion of security vulnerabilities are due to incorrect invocations of library functions, which means we need a more rigorous reasoning about library function specifications. However, currently, library function specifications are specified empirically. For example, now we know format string attack, so now it is clear that printf, the first argument, should not be a user-specified string. And for string copy, the source buffer should not exceed the boundary of the destination buffer, and these two buffers cannot overlap. And when you free a buffer, this P should be obtained from a previous malloc, and also P cannot be freed before, etc. So every function seems to have quite different specification. Now the question is, what is a unified reason why these specifications are required? So based on the notion of pointer taintedness, the answer is very simple. They are required to eliminate pointer taintedness. So now this is, I think this is a very interesting observation because now the extraction of security specification of a function is reduced to a theorem proving task. We basically only need to reason about the conditions under which pointer taintedness exists. So in this project, we use theorem prover to analyze the code in order to extract such specifications. And the benefit of formal and complete specification is that it allows compiler techniques to check application source code for security. The basis of the basis of the theorem proving technique is a formal definition of program semantics. So currently we use we define the semantics using an equational logic framework, but due to time constraint, I'm not able to show the equational definitions of the semantics. But basically we defined two sets of equations. The first set defines a taintedness-aware memory model, where we defined two operations to fetch the content and test the taintedness of each memory location. And then the second set of equations incorporate the notion of pointer taintedness into program semantics. For example, we define the semantics of load, store, and ALU instructions in order to propagate taintedness from source data to destination data. And also we define the semantics of input functions like scanf, receive, and receive from to initially taint the memory locations. So now having the formal semantics, this is the flow of theorem proving technique. The first, a piece of the C source code of a library function is automatically translated to its formal semantic representation. Then for each pointer dereference in an assignment, we need to generate a theorem stating that the pointer should not be tainted. So we get a bunch of theorems in this stage. Then finally, we use a theorem prover to prove the validity of the theorems. So either these theorems can be proved, which means the library function is secure unconditionally, or these theorems cannot be proved by the theorem prover. In that case, the theorem prover will suggest a set of sufficient conditions that imply the validity of the theorems. So those conditions are the security specifications of the analyzed function, which shows that as long as these conditions are satisfied, then this function is secure. Exactly the security specifications. Now here is an example of VF printf. In this part, in the program, there are two pointer dereferences in the code, in the assignment statement. Corresponding to the first one, we need to prove that buff plus n should not be a tainted value. And corresponding to the second one, we need to prove that Q should not be a tainted value. Then we tried to use the theorem prover to prove these theorems. But initially, we cannot establish the proof because the two theorems are only valid under certain preconditions. Then what we do is to add these preconditions as axioms to the theorem prover and repeat this step until both theorems are proved. So finally, we found that four preconditions are added to the theorem prover, which are the security specifications of VF-printf. So these are the extracted security specifications, which means if all these are satisfied, then VF-printf is secure. An interesting observation is the last one, which states that no locations within AP activity range are tainted before VF-printf is called. So this AP activity range is the memory location that the AP sweep over. So this specification exactly indicates the scenario of the format string vulnerability that I just showed you before in a previous slide. I'm sorry? Okay, so I use theorem prover. So the theorem prover is currently not a completely automatic tool. But it substantially helps you to go through the complicated formal reasoning process. It's really very helpful, and the theorem proving process is an interactive process. Yeah. So using similar technique, we analyze string copy, where we extract specifications indicating buffer overflow, buffer overlapping, and buffer underflow scenarios. And to analyze the function free of a simplified heap management system, we extract security specifications indicating heap corruption vulnerability. And we also use this formal reasoning to analyze the socket read functions of Apache and the third-party HTTP server, where we can prove that the Apache function is free of pointer taintedness, and two vulnerabilities are exposed in the theorem proving process of this third-party server function. So so I have shown that formal reasoning of pointer taintedness allows us to expose potential security vulnerabilities. And in this project, we developed a runtime pointer taintedness detection technique to defeat memory corruption attacks. So this is basically a processor architecture level mechanism to detect pointer taintedness. So the idea is exactly the same as our previous paper, but the only difference is this is a runtime detection technique, and it is not based on theorem proving or static analysis. But the goal of this project is to show the validity of pointer taintedness concept on whole programs of real applications. So we run many network servers and spec 2000 integer benchmarks on this modified. By the way, this is implemented on simple scalar simulator. And so we evaluate the effectiveness of detection by using both control data attack and non-control data attack. And we found that both attacks are detected in a uniformed way. Because from the standpoint of pointer taintedness, these two types of attacks are not different. Both are pointer taintedness attacks. We did not find any false alarm in the application evaluated, which means whenever there is no attack, there is no alarm. Another advantage of the another advantage of the technique is the transparency to applications. And we can run pre-compiled binaries on this processor, the modified processor. But there could be a small number of potential attack scenarios undetected. However, we argue that these scenarios are really very rare, and they are not defeated by any current generic protection techniques. So based on this evaluation, we conclude that pointer taintedness detection can be applied to the whole program of real software, which offers a substantial improvement on security protection. The impact on performance, so right now this is implemented as at the processor level. So we assume that this works pretty well in parallel with the current architecture. So we think the performance overhead should not be very big, but we haven't done very extensive analysis on this. Correct. Okay, so that I only modify the system call, the receiving system call, which is implemented in simple scalar. So yeah, yes. So I think yeah. So currently, a challenge of this technique is how can you convince, for example, Intel people to do this, because you need a different memory model. So that should be, hopefully, should be addressed in my future research, I think. And so. Yeah, parity bit, yes. Yeah. But the goal of that project is to test the concept that pointer taintedness concept can be applied to real large piece of code, the whole program of real code, and including network servers, FTP servers. So now I reach to my conclusion. We have shown that many real-world software can be compromised by corrupting non-control data. So therefore, it is insufficient to rely on control flow integrity for software security. Then, on the other hand, we found that pointer taintedness is a unifying perspective to reason about most memory corruption vulnerabilities and attacks. And we argue that reasoning about pointer taintedness is a promising direction to enhance security on real-world systems. To demonstrate this, we developed a theorem-proving-based code analysis technique and a runtime pointer taintedness detection technique to defeat most memory corruption attacks. And I think the current state of my research is a good basis, and I would like to extend it by providing a higher degree of automation for the theorem proving technique, because it is currently a lot of interactions, and also to reduce the intrusiveness of a runtime pointer taintedness detection technique. Hopefully, by combining these two techniques, I do not need the extra bit, because if I can reason about the preconditions of each function, then the architecture can only check the validity of the preconditions without the extra bit. But this is the hope. And for long-term goals, I think there are a number of interesting directions. The first is to extract programming styles susceptible to security attacks. So, for example, we observed that a big problem in current programming practice is the long lifetime of security critical data. So how can compilers detect such bad programming styles in order to mitigate the security impact? Then to identify a broader range of non-traditional security threats and to study historical data about how security vulnerabilities were discovered, reported, and patched to see how successfully we did in the past and what should we do in the future. Another very interesting thing I like to do is to decompose the behaviors of virus, worms, and rootkit to a number of basic building blocks. So as you can see that in my study, I tried to decompose security vulnerabilities to a number of building blocks. And that really helped me to think of what is the maximum capability of attackers, whether the attacker, how the attacker can reassemble polymorphic attacks to understand what is the real threat to our systems. And finally, I have a few words about my research methodology. As I said in my first slide, that the uniqueness of my research is the analysis-centric approach. I spent a significant amount of effort in my dissertation on analysis of real data. So the methodology is to start from reality to define the problems. And I really like this methodology. And I like to analyze real data and real instances. And sometimes I have to say it is tedious, but I believe this is a step towards a lot of fun in research. And also, it is definitely rewarding, especially for systems research. And I think the eventual goal is to strongly motivate the research topics that solve problems in the reality. So this concludes my talk. And,
how would, say, an ordinary dev sit down to analyze some function to determine the properties of it?
I'm sorry.
How would I explain to an ordinary, working developer how to do this, or is there some way to automate these properties of a function?
To automate the property of functions, to automatically extract the specification. Yeah, so that is what I was trying to show by reasoning about pointer taintedness. We can extract a lot of security specifications. Does this answer?
I'm sorry. I'm sure I didn't ask my question very well. So, one of the things that I'm thinking about is the next step, which is to take your interesting work and how it can be put into practice. Mm-hmm. And so I'm wondering if you've given thought into ways to. You point out, for example, in your own slide that this is tedious. So, of course, as a programmer faced with something tedious, I see you write a program to remove the tedious.
Yeah. So I think the excitement, if I can get the job, then the thing is, I think a PPRC is definitely a very strong team in this type of research. So they can find they are very strong in formal reasoning and compiler techniques. But I think then the input I can put into their technique is I show that what to check. What should be the starting point that you can build your formal reasoning on top of that. And this thing in my dissertation, I think pointer taintedness is a property that it is critical to check. So I think so to automatically reasoning about this, we need to take the direction similar to PPRC direction, so like model checking, like theorem proving, that type of things.
We ask the question in a different way. So it's not the case that your research has reached the status where you can come in and give a class to junior developers, and the next day everybody knows how to do that.
No. So my contribution is basically the extensive analysis, which tells you what to check, what is the critical program behavior that can pretty much ensure security. So.
Any other question? No?
No.
Thank you.
Thank you very much.
Get something to eat?
Yeah.
Who was lunch?